In the last video in this series, number 5, we continued to look at a flat two-dimensional surface and investigated making measurements of it using 3 particular frames of reference. We were introduced to the idea of the metric tensor GMN for each reference frame, which in the Einstein summation convention form is shown here equal to the product of the basis vectors of the reference frame. The latter basis vectors are shown in bold to indicate their vector nature, although their dot product entries in the metric tensor here are obviously scalars. And we can show what this all looks like for the 2 dimensions by writing it in matrix form. For each of the 3 frames of reference which were discussed, we applied the previously derived formula for the square of an infinitesimally small displacement ds in terms of its contravarying components dx1 and dx2. That formula in the Einstein summation notation is ds squared equals dxm dxn gmn. And when expanded in 2 dimensions, it looks like this. Now from this formula, we were able to identify the 4 elements of the metric tensor for each of the 3 two-dimensional frames of reference, and we found the following. Firstly, for the Cartesian coordinate system, the metric tensor was found to be 1, 0, 0, 1. And so for this, ds squared turned out to be the same as would be obtained by Pythagoras, namely, in 2 dimensions, ds squared equals dx1 squared plus dx2 squared. Secondly, if a similar frame of reference but with the axes at an oblique angle alpha to one another was used to measure that same flat surface, then the metric tensor was found to be 1 cos alpha 1. When this was used in the formula for ds squared, it reduced to something slightly different from Pythagoras. ds squared equals dx1 squared plus dx2 squared plus 2dx1 dx2 cos alpha, but was easily seen to be related to the cosine rule for the addition of 2 vectors, in this case displacement vectors. And finally, we considered making measurements of the same flat surface using polar coordinates. And for that frame of reference, we found that the metric tensor was 1, 0, 0 r squared. This meant that the size squared of an infinitesimally small vector ds would be measured to be given by ds squared equals dx1 squared plus r squared dx2 squared. Or using the more usual r and theta instead of x1 and x2, it is ds squared equals dr squared plus r squared d theta squared. Having therefore found the metric tensors for 3 frames of reference which can be used to measure a 2-dimensional flat space, we next want to consider briefly the metric tensor of a frame of reference used to measure a very simple curved surface. Perhaps a good example of such a curved surface is to consider the surface of a sphere. This surface, as opposed to the volume of the sphere, this surface is clearly 2-dimensional, in the sense that you would only need 2 numbers to determine a position on the surface. However, we can talk in terms of this 2-dimensional surface being embedded in a 3rd dimension which we, as outsiders, can appreciate. If you like, we have a sense of perspective in this diagram. And not only that, we can also say that the surface of this sphere is curved. There's no way it could be flattened out even by bending it or flexing it. Now, we haven't really defined what we mean by curved, but from our simple discussion in video number 3, we would say that the 2-dimensional surface of the sphere is not simply a flat sheet which has been bent or flexed. If you wanted to start with a thin, flat sheet of metal, say, and make a sphere, you'd have to hammer it and stretch it and distort it. Similarly, if you went the other way around and started with the sphere, there's a sense that if you tried to make it into a flat sheet, it would be impossible. It would crinkle and overlap unless you could somehow compress it into a flat sheet. The surface of a sphere is a truly curved surface in that simple sense of the word. Let's imagine making sensible measurements of position on the surface of such a sphere. The obvious candidate for a frame of reference in which to make those measurements would be what we call spherical polar coordinates. However, that system in its fullness is really for making measurements in 3 dimensions. In other words, for measuring position anywhere inside and outside of the sphere, as well as on the surface of the sphere. In that full use of the spherical polar coordinate system, you need three numbers to determine a position in those three dimensions. On the other hand, we're thinking of it as a two-dimensional surface, not a volume, and so we only need the surface investigating. We need therefore to modify the spherical polar coordinate system slightly for the two-dimensional surface. You may recall that for the three-dimensional use of this system, the three numbers needed to determine a position anywhere inside or outside of the sphere are as illustrated in this diagram, there being one distance measure, r, and two angle measures, theta and phi. R is clearly the distance from the centre of the system to the point being measured, in other words the radius, and in our case it will be the distance to the surface of the sphere, and therefore it will be a constant and not one of our variables. As far as the angles are concerned, it has to be said that physicists and mathematicians are not always consistent in the way these are chosen or labelled in this kind of system. We will use what seems to be the most common standard. Phi is the azimuthal angle, which for the Earth would represent longitude. It's the angle measured horizontally from a given equatorial radius. Theta, on the other hand, is the polar angle or inclination, which is measured here from the top pole, the North Pole, downwards, and is a bit like latitude, although in fact geographical latitude is measured upwards from the equator. No matter, these three numbers, r, theta and phi, as we show them here, specify a point in three-dimensional space and could be used instead of three-dimensional Cartesian coordinates x, y and z, or x1, x2, x3, to make measurements in that space. However, if we are only considering the two-dimensional surface of this sphere, then the radius r is constant. It's the same for all points on the surface, and so it's theta and phi which represent variation within the two dimensions of the surface and which will determine position on that surface. They become our x1 and x2 for this two-dimensional coordinate system, which we will simply call surface spherical coordinates. The radius r is important, of course, and in a way we could say it determines the actual curvature of the surface, although we still haven't yet given a strict definition of that word curvature. Given all this, the two dimensions of the spherical surface, x1 and x2, will be taken to be theta and phi, and again we'll leave this box here as a reminder. It's worth reminding ourselves at this point that so-called beings on such a surface would not be aware of the third dimension or any bending of it visually. They would not see the curvature which we see in the perspective of the diagram. To them, there would still only be a seemingly, dare I say it, flat surface to move around on. The bending, even of them on the surface, would not be sensed, except that certain experiences and experiments would perhaps show it up. For example, walking in a dead straight line would eventually bring them back to the same point on the surface as they travel round the whole surface. And other experiments too, which we'll mention later, would demonstrate to them that the surface was actually curved. So, what is the metric tensor of the surface spherical coordinates which we're going to use to make measurements on this two-dimensional curved surface? Well, it's fairly easy to calculate, although we won't go through all the details. You simply imagine a small displacement vector ds on the surface, which must obviously involve a small change d theta in theta and a small change d phi in phi. And then you use basic geometry to work out the value of ds squared in terms of d theta and d phi, and of course the constant r. And when you do all that, you get this equation. ds squared equals r squared d theta squared plus r squared sine squared theta d phi squared, which if you want to see it in terms of x1 and x2, would be this: ds squared equals r squared dx1 squared plus r squared sine squared dx1 dx2 squared. But we'll stick with the theta phi version for the time being. Now there are a couple of things to notice about this equation. First, there are no cross terms in d theta times d phi. There are only d theta squared and d phi squared terms, which are essentially dx1 squared and dx2 squared. So the metric tensor will not have any off-diagonal terms. If you like, all the off-diagonal elements will be 0. Another thing to notice, of course, is that we have for dx1 and dx2 the variables d theta and d phi, neither of which have units, and yet we have a distance squared on the left. No doubt you realise by now that the unit will be accounted for by the presence of the r squared, which multiplies each term here. This relationship, which we haven't proved but can easily be found from the geometry and which we will just assume, must be the same as our known formula for ds squared, which applies in any frame of reference and in any space, namely, in the Einstein summation convention, ds squared equals dxm dxn gmn. And this formula, if expanded over the two dimensions, gives us, as before, this expression. Now, getting rid of the middle terms, which we know must be 0 from the expression I said you'd get if you worked through the geometry, we need now to compare these two equations. Our standard formula for ds squared with that from the geometry, remembering that dx1 is d theta and dx2 is d phi. Doing this, you can see that g11 is r squared and g22 is r squared sine squared theta, which means that as the cross terms are 0, the metric tensor for the curved surface of a sphere must be r squared 0, 0 r squared sine squared theta. Of course, given the fact that r is a constant property of the space, the only variable within this metric tensor is theta, which appears in g22 in the form of sine squared theta. In other words, this particular metric tensor is not constant over the whole of the space, over the whole of the surface of the sphere. It varies from place to place, at least in one of its 4 entries, and that variation is for different values of theta. If you think about it, you could fancifully say that we have equimetric lines in the two-dimensional space, lines of constant theta, the angle coming down from the top pole. So the metric tensor is the same along lines like these, shown in blue, but they are different from one line to another. Just in case there's any confusion, it's perhaps worth mentioning again that we're talking here about what I am calling surface spherical coordinates to measure the two-dimensional curved surface on a sphere. When we talk about spherical polar coordinates, normally we start with the same kind of diagram, but in that case r is not constant, of course, and we use these 3 coordinates, r, theta and phi, to measure position in 3-dimensional flat space, just as we'd use x, y and z in 3-dimensional Cartesian coordinates to measure that flat 3-dimensional space. In spherical polar coordinates, we would say that r, theta and phi become x1, x2 and x3, and it's actually not too difficult to show that the metric tensor for 3-dimensional spherical polar coordinates would be given by this: 1, 0, 0, 0 r squared 0, 0, 0 r squared sine squared theta. Notice that this bit is the same as the two-dimensional surface spherical coordinates. This is the theta and phi part. This bit is from r, which means it's fairly straightforward. What it measures is what you get, the radius. You don't have to take anything else into account. Referring back to this idea of 3-dimensional spherical polar coordinates will be useful when we come to discuss the Schwarzschild metric for a black hole when we get to General Relativity in video number 13. Anyway, to sum up here what we've been saying about two-dimensional surfaces, let's remind ourselves of the 4 frames of reference and the 4 spaces that we've been considering. 3 for measuring within a flat two-dimensional space and 1 for measuring within the curved two-dimensional space of the surface of a sphere. Firstly, Cartesian coordinates in a flat two-dimensional space gives us a metric tensor of 1, 0, 0, 1. Secondly, oblique coordinates with angle alpha in a flat two-dimensional space gives us a metric tensor of 1 cos alpha 1. Thirdly, polar coordinates measuring a flat two-dimensional space gives us 1, 0, 0 r squared. And finally, surface spherical coordinates in a curved two-dimensional space, the surface of the sphere, with coordinates theta and phi, gives us a metric tensor of r squared 0, 0 r squared sine squared theta. Looking at these four metric tensors, we could ask a number of questions. For example, what is it about the first three of these metric tensors, or frames of reference that they represent, which makes them able to make measurements of flat spaces, flat surfaces? Are all three of them basically saying the same thing about the space, that it's flat? Is there something about these first three metric tensors that makes them, at least in some sense, the same? And also, of course, we could ask, what is it about the fourth metric tensor here and its frame of reference that makes it able to make measurements on a curved surface, namely, in this case, the surface of a sphere? How is it different from the others? Now, without trying to answer those questions, all we can really say at this stage is that each one of these four metric tensors contains all the information, all the important information about the particular frame of reference that they each represent. They will each allow you, for example, to home in on any point in the particular space and then work with the axes at that point. Those axes will effectively be straight lines as you approach the point, and so you can work with the contravarying components of the vectors on those axes at the point to find the size of the resultant vector by using a formula similar to this one for a displacement vector. And that idea or concept is true for the metric tensor of any frame of reference and any space. For example, suppose we had a two-dimensional space, it may be flat or it may be curved, and we were using curvilinear coordinates to measure it. If the space is curved, then we would obviously have to use curvilinear coordinates, but if it was flat, we would be free to use them if we wanted to, but wouldn't actually need to. Whatever the kind of space, suppose we were using curvilinear coordinates, and they look like this. Then, providing you knew the metric tensor as a function of position in the space, in other words, GMN as a function of position, you would know that this equation for ds squared could be applied to any point in that space. Now, you may of course say that this equation is really rather limited in that it deals with an infinitesimally small displacement vector ds rather than the macroscopic vectors of the real world. However, as we develop things further in terms of differential geometry, you'll begin to see the sense in which the metric tensor and what this particular equation leads to is crucial in relation to curved spaces and to gravitation. However, before we explore further some of the ideas of differential geometry, it's probably worth focusing just a little more on the metric tensor and the whole idea of curvature. Early on in the discussion of gravity, we toyed with the idea of different frames of reference which we used to measure the same space. And in that case, they were moving frames of reference. We could have been doing physics experiments while travelling on a train or while standing on the platform of a railway station. We were imagining things that exist in the space, but undertaking those measurements in a couple of different ways, or rather within different frames of reference. The point was made early on that there would be a need at some point to consider how measurements made in one frame of reference could be converted to measurements of exactly the same situation made using another frame of reference. So let's now discuss this kind of thing in a little more detail, and we will see that it should lead us to a better idea of what we mean by the word curvature. Imagine that we're using a set of Cartesian coordinates to measure the positions of things in a flat two-dimensional space, shown here in red with the axes x1 and x2. Suppose also that we are focusing on a single point in that space, the point shown here as a black dot. We could be looking at a vector at that point in the space and be interested in its components, so we could simply be monitoring something that happened at the point. The 0 of the reference frame has been included in the diagram for completeness. Clearly the measurement of the position of the point here would be given by the coordinate measures x1 and x2 as shown here in red. Now I apologise for the fact that we have the same thing for the label of the axes x1 and x2 as well as what we might call the coordinate measure x1 and x2 for the point, but I think you get the situation. I'm assuming that these measurements have been found by taking parallel lines to the axes, and if we're talking vectors, these would relate to the contravariant components. But of course with Cartesian coordinates it doesn't really make any difference. Now suppose we wanted to make measurements of this exact same position, this spot in the same space, but this time using a different frame of reference. We'll consider using the angle coordinates which we've used before, where the angle between the axes is alpha. This angled measuring system is shown here in blue, with its axes in the tilde version, x1 tilde and x2 tilde. Let's now measure the position of this spot using this frame of reference, and once again take the coordinate measures by drawing parallel lines to the axes. This would be the equivalent of taking the contravariant component of a displacement vector from the origin, but we're using it simply here to find the position of the spot. If we did this, we would obviously get different values for x1 tilde and x2 tilde compared to the red x1 and x2. Again, I apologise that they look the same as the axes labels. However, it should also be obvious that these two particular frames of reference are so simple that we should be able fairly easily to convert all the red x1, x2 measurements made by the Cartesian frame into the blue x1 tilde, x2 tilde measurements of the same point made using the angle system, and vice versa. We should be able to work out the equations that will perform the conversion from one to the other, from the red measurements to the blue, or the other way around from the blue to the red. Let's superimpose both sets of measurements onto the diagram by adding a little bit of the red frame to the blue, and then add the various black dotted lines that indicate the contravariant components, 2 for blue and 2 for red, although in fact the dotted line parallel to the horizontal axis is common to both. Again, it should be obvious that generally speaking, one of the component measures in one frame is likely to be some function of both the measures from the other. In other words, the blue x1 tilde is likely to be some function of both the red x1 and the red x2 measurements, and similarly for x2 tilde. Mathematicians might write such a set of conversion equations like this. Now I recognise that this kind of thing can be confusing for some students at first with these repeated x tildes. But it's simply saying that the measured x1 tilde value at some point in the blue frame will have to be some function x1 tilde of both the values x1 and x2 for that point as measured by the red frame. And the same applies of course to x2 tilde, which is also likely in most cases to depend on both x1 and x2 via a different function x2 tilde. These are functions. And these are values. We could of course equally well say that there must be a set of inverse functions which would take us back from the blue angled component measures to those of the red Cartesian frame measures. And this could be written like this. x1 measured in the red Cartesian frame must be some different function x1 of the measurements of x1 tilde and x2 tilde in the blue angle frame, and so on. But what are these functions which allow us to go from one of these frames to the other? Is it possible to find them? Well, in the simple situation that we just looked at, of course, it is, and it's an easy exercise to find out. Here are the answers if you care to do the basic geometry of chasing the right-angled triangles in this diagram and using the fact that the angle between the axes is alpha. The functions for going from measurements in the red Cartesian frame, x1 and x2 measurements, to the blue angled measurements, x1 tilde and x2 tilde, are x1 tilde equals x1 minus x2 divided by tan alpha, and x2 tilde is x2 divided by sine alpha. And if you want to go backwards in the other direction, from angled to Cartesian, the conversion equations are x1 equals x1 tilde plus x2 tilde cos alpha, and x2 is x2 tilde times sine alpha. Now you might wonder why we've done this here. We don't need to know these kinds of conversion equations right now, but there is a very important point to realise from all this. What we've just done is to find a way of converting the measurements made by one frame of reference with its particular metric tensor to those made by another frame of reference with a different metric tensor. We first went from this Cartesian frame with its metric tensor to this angled frame with its metric tensor using these conversion formulae. And then we went back from the angled to the Cartesian using these formulae. It may seem trivial, but that last conversion back to Cartesian coordinates is a very important idea. Being able to do this, being able to take the measurements of some system, in this case the blue angle system, into those of a Cartesian system, in a sense, demonstrate that the space being measured is flat. To put it rather crudely, the ultimate or simplest frame of reference for a flat two-dimensional space, like the screen on which you're seeing this, is that of Cartesian coordinates, and in that case the metric tensor for that reference frame is the identity matrix 1, 0, 0, 1. It is, in a way, the simplest way of describing or measuring a flat space. And this means that if we have a frame of reference, it may even be a curvilinear frame of reference, and if it's measuring some space, and if we're unsure whether or not the space it is measuring is flat, we have a way of testing for flatness. Namely, if by a coordinate transformation of our frame of reference we can produce a different frame of reference whose metric tensor is the identity matrix, then the space being measured must actually be flat, no matter how we choose to measure it. In other words, if we can convert the measurements to those of a Cartesian frame, then the space must be flat. Suppose, for example, you had a weird and wacky frame of reference for a two-dimensional space which looked like this. We'll think of it as the tilde frame and we'll draw it in blue because we will want in a moment to see if we can change it legitimately back to the red Cartesian frame. I suppose you just didn't know whether the space it was measuring was flat and somebody had simply drawn a curvilinear reference frame on it, or whether the space was really distorted or curved in some way which you can't see, and so it had to be measured using curved coordinates. Perhaps you're a two-dimensional being on the space and you don't have the benefit of a perspective view like this, which would tell you that it was curved or it wasn't. In that situation, provided you know the metric tensor for that particular blue curvilinear system of coordinates, which in this complicated case of wavy lines would be some function of position, a function of the x tildes, and provided you can find equations which apply everywhere in the space, which will convert the x tilde measurements of that space into the x measurements of Cartesian space, such that when you made this transformation you ended up with the identity matrix for its metric tensor, then you can say that the space is flat. And it's not really like this. It is genuinely like this. And it doesn't matter that somebody has drawn a strange looking set of curvilinear axes on the space. The fact that the blue x tilde measurements from it can be converted to new red x values within a different frame of reference which has this very simple Cartesian metric tensor with ones in the diagonal and zeros everywhere else, means that however you choose to measure the space will always be flat. If, on the other hand, you have your two-dimensional space with curvilinear coordinates on it, and it is impossible to find a set of equations that will convert the measurements made using that frame of reference into ones which would be given by simple Cartesian coordinates with the identity matrix as its metric tensor, then the space is said to be curved and could look something like this, even though you have no insight into the perspective. That idea of changing into a Cartesian system if possible is probably the best definition, or rather illustration, of the meaning of curvature so far. Let me reiterate. Suppose you had a scenario where you have a space and a frame of reference that successfully measures positions in that space, but you don't know whether the space itself is flat or not. If, however, you can find a coordinate transformation to a new frame of reference, such that the metric tensor of that new frame is the identity matrix everywhere in the space, then the space can be said to be flat everywhere. If you can't find such a transformation, then the space must have some curvature in it, either in all of it or even in only part of it. We'll consider a particular case of this kind of thing in a moment, but before we do, we should say that the same is true for higher dimensional spaces. Even though we find it difficult to picture a three-dimensional curved space, mainly perhaps because we couldn't visualize any fourth-dimensional perspective, hopefully we accepted the fact that three-dimensional space could, in some way, be curved or stretched. So imagine we had a three-dimensional space, shown here in blue, with the x tilde axes, but we couldn't know on the face of it whether or not the space was curved. It's been illustrated with curvilinear coordinates here, with x3 tilde not being shown but somehow coming out of the screen. This space could be curved or it could be flat. However, providing we knew the metric tensor of these curvilinear coordinates for the frame of reference being used to measure the space, and we knew it as a function of position in the three dimensions, and provided we could find a set of transformation equations or functions for the x tildes which would convert those three blue x tilde measurements into those of a new red frame of reference with values x1, x2, x3, such that its metric tensor simply had ones in the diagonal and zeros everywhere else, then we could be assured that the three-dimensional space was flat, and it wouldn't matter what coordinate frame had been chosen to measure it. But let's go back to 2 dimensions to consolidate this whole idea just a little bit further, and this time we'll consider simple polar coordinates. The reason we choose them is because they are curvilinear coordinates, but they can be used to measure a flat space. The basis vectors in polar coordinates stretch and compress in quite strange ways. Well, one of them does anyway, the theta or x2 coordinate, and yet polar coordinates describe and measure flat space. The question here is, can we use what we've just learned to show that the space which is being measured successfully by curvilinear polar coordinates must be flat? Well, we know the answer must be yes, because we've tended to assume that polar coordinates apply to flat surfaces. They're drawn on a flat piece of paper. But let's look at the problem as if we didn't know. After we've checked polar coordinates, we'll then look at surface spherical coordinates applied to a surface of a sphere, and in that case you'll probably realise that it should not be possible to find conversion equations, because our assumptions is that the surface of a sphere is a two-dimensional curved surface. Anyway, let's check them both out briefly. First of all, polar coordinates, and we'll check them out rather quickly and simply. Here is the polar coordinate frame of reference in blue, and we'll take a point in it and mark it with this black dot. The 2 polar coordinates are clearly the radius r from the centre, which will show as a blue radial arrow, and the angle theta measured from a particular axis line, which we'll illustrate using this curved blue arrow. We're showing the measured value of r here as x1 tilde and the measured value of theta as x2 tilde in this blue frame of reference. If we now overlay this with part of the Cartesian frame in red, which is what we want to try to convert things into, we can draw lines parallel to those axes to show the components of the black dot in that red Cartesian frame, and these are labelled x1 and x2. So the first thing we need to do in order to check whether this space being measured by the polar coordinates is flat is to see whether we can convert the blue x1 tilde and x2 tilde measurements of the polar coordinates into the x1 and x2 measurements of the red Cartesian frame. Looking at this, the equations relating the measurements in the two frames are fairly obvious. We would normally say x equals r cos theta and y equals r sin theta. But with our renaming, that becomes x1 is x1 tilde cos x2 tilde and x2 is x1 tilde sin x2 tilde. So fairly obviously we do have a set of equations which can convert from polar coordinates to Cartesian coordinates. The Cartesian frame of reference has the identity matrix for its metric tensor, and so that means the space is flat. It doesn't matter how we decide to measure it, and that was a bit of a waste of time really, but now let's consider what we've been calling surface spherical coordinates on the two-dimensional surface of a sphere. In other words, on a sphere with a radius r, which has a fixed value. Here's the situation as we showed it. The angles phi and theta are the two variables which describe position in this two-dimensional spherical surface, the radius r being a constant for the particular sphere. Theta and phi would then be our x1 tilde and x2 tilde blue coordinates. The metric tensor for the two-dimensional surface of a sphere, which was stated earlier but we didn't actually prove it, is r squared 0 and 0 r squared sine squared theta. Or with x2 tilde instead of theta, it would look like this: r squared 0, 0 r squared sine squared x2 tilde. The question being posed is, can we find a set of equations which will convert from the theta phi system, which is the blue x tilde system, to a Cartesian system, the red x1, x2 system? If we could, then we could say that this is really a flat space which has simply been bent or flexed into a sphere. But of course we know that in practice you cannot flatten a sphere out. And so it should be no surprise that however hard we might play around with the mathematics, we cannot find a set of equations that will convert from the theta phi system to a simple Cartesian system, in other words from the blue x tilde system to the red x system. It is impossible to find equations like these such that the new red x1, x2 system represents the Cartesian coordinate system with the identity matrix as its metric tensor everywhere in the space. And that really illustrates our current best definition or illustration of what we mean by a curved space. If the coordinates used on a particular space cannot be transformed to a new frame of reference such that its metric tensor becomes the identity matrix everywhere, then the space itself must be curved in some way. And that applies for 2 dimensions, where you have to try to make the metric tensor look like this, or for 3 dimensions, where it must look like this, or for as many dimensions as you like. Now at this stage you may justifiably say that given a complicated frame of reference and its associated metric tensor, it could take a ridiculously long time to check all possible conversion formulae to see if we could find a frame of reference that could be said to have the identity matrix as its metric tensor everywhere. In any case, how can you know that you've tried every possibility, especially in situations where the mathematics might be extremely complex? Of course, that's a very good point. What we've just stated about curvature is okay for a reasonable working definition or illustration, but what we really need is a quicker and easier way to test whether a particular space is curved or not, either in its entirety or simply just parts of it. And all of that will be discussed later when we begin to think about how we can quantify curvature. How we can find a number or an array of numbers that we can use to describe the amount of curvature at a point in space. But before we move on to exploring more in that direction, it might be worth consolidating some of our ideas about the metric tensor so that we get a sense of how simple it is, at least in principle. We recognized, I hope, that even with a flat two-dimensional space, the metric tensor for the frame of reference being used could, in principle, have different values of its g11, g12, g21, g22 at every point in the space. Even though simple Cartesian coordinates could have been used on that flat space, we could be using a set of overcomplicated curvilinear coordinates to measure things. And that could mean that the 4 values in the metric tensor varied from position to position in the space. At a single point in 2 dimensions, of course, these 4 values would be fixed at particular values for that situation. And if we were to home in on that point, we would see that even with curvilinear coordinates, the coordinate lines could be said to be straight in that infinitesimally small region. Granted, the basis vectors at that point, e1 and e2, could be greater than, equal to, or less than 1, depending whether they were being stretched or compressed at that point. And also the angle alpha between the lines could be anything between 0 and 180 degrees, but at least we can say that the lines would be straight and the angle would be fixed in that small region. Here's a picture of such a general situation at a point, where the point in space is marked with a black dot. As stated, as we have 2 dimensions here, the metric tensor at this point would have 4 fixed values, even though in the rest of the space the values might be very different. But what can we say about these 4 numbers for this particular point? Well, g11 at the point must be given by the dot product of e1 with itself. The dot product is the magnitude of one vector times the magnitude of the other times the cosine of the angle between them, and the angle between them in this case is 0. They're the same vector, and cosine 0 is equal to 1. So we're really saying that g11 is the magnitude squared of the basis vector e1 at that point. And similarly, of course, g22 is the magnitude squared of the basis vector e2 at that point. So g11 and g22 are all about the sense in which the frame of reference is stretched or contracted at the point. They could each be separately greater than or less than or equal to 1, depending on how each axis is stretched or contracted. So let's think about another entry in the metric tensor, say g12. Well, we know that it's given by the dot product of e1 with e2, and so also is g21. They are actually both the same as each other. The order of terms in a dot product is immaterial, we've said that before. As to what they mean, well, the dot product being the size of one vector times the size of the other times the cosine of the angle between them, means that the value of these two depends linearly on the stretch of each of the basis vectors at the point and on the cosine of the angle between them at the point. So we can say that for the metric tensor at any point in a two-dimensional space, the 4 entries can be summarized like this. This is the square of the E1 basis vector at the point. If it's 1, there's no stretching in that direction. Greater than 1 means some kind of expansion, and less than 1 means contraction of that axis. Similarly, this is the square of the E2 basis vector at the point. If it's 1, there's no stretching on that axis, and so on. This, however, and this, for the same thing, is a bit more involved. It is a measure of the stretching of each of the axes at the point and the cosine of the angle between those axes. If you think about it then, there are only really 3 pieces of information in these 4 metric tensor values at a point in two-dimensional space. There is stretch 1, stretch 2, and angle. Also, there are only really 3 numbers in the metric tensor. This, and this, because these two are the same as one another. 3 pieces of information and 3 numbers. Now, although manipulating metric tensors can be a real headache, I hope that this rather basic discussion will help you to see that the information which the metric tensor contains is really rather simple. Let's check out this whole idea by looking at a few familiar two-dimensional frames of reference. Firstly, for Cartesian coordinates measuring a flat two-dimensional space, this is what we found. The metric tensor for two-dimensional Cartesian coordinates has the same 4 values everywhere in the space, and they are 1, 0, 0, 1. Let me adjust that statement. The metric tensor has the same 3 values everywhere in space because 2 of them are always the same. We can say that because the metric tensor in this case is the same everywhere. Every point in the space has the same three numbers in the metric tensor, and we know they are 1, 0, and 1. The G11 being 1 means there is no stretching of the basis vector E1, and similarly for E2, they are unit vectors everywhere. The G12 being 0, and the G21 of course, is a consequence of the angle between the axes being 90 degrees everywhere. Cos 90 is 0. The three pieces of information for this two-dimensional frame are therefore no stretching of the E1 anywhere, the size is 1. No stretching of E2 anywhere, the size is 1. Angle between the axes is 90 degrees everywhere. Cosine angle is 0. Okay, that's for the two-dimensional Cartesian frame of reference and flat space. Now let's look at how this way of interpreting the metric tensor works out for other frames of reference measuring a two-dimensional flat space. We'll next look at the oblique coordinates. Oblique coordinates at an angle alpha to one another. This time, although the frame of reference is different, it is still the same everywhere in the space. There are no wavy lines here. Also, once again, we will assume there's no stretch of E1 or E2, so we have 1s here and here for their dot product with themselves. However, for this, G12, which is of course the same as G21, we know that it is the dot product of the two basis vectors, and therefore equal to the product of their sizes multiplied by the cosine of the angle between them. The sizes in this case each being 1, we can say that for this oblique reference frame, G12 must be cosine alpha, and it must have that value everywhere because the angle between the basis vectors never changes throughout the space. So that should all make sense. Three pieces of information for two dimensions. No stretching in E1 anywhere, the size is 1. No stretching in E2 anywhere, size is 1. And the angle between the axes is alpha everywhere. Let's now check out polar coordinates, again applied to this flat two-dimensional space. Polar coordinates r and theta for x1 and x2. This is what we had for the metric tensor from our geometrical analysis of the flat space using polar coordinates. Does our new way of interpreting the metric tensor make sense for this? The 0 here for G12 and of course for G21 must mean that from our formula that the dot product of E1 with E2 is 0. Now remember that the dot product can be thought of as the size of one vector times the size of the other times the cosine of the angle between them. The sizes of E1 and E2 are not 0, but of course the cosine of the angle between them is always 0 in this space because the radius always intercepts the circumference at 90 degrees everywhere. So that sorts those two out. But what about the first entry in the metric tensor, G11 equals 1? Well, we know that G11 is the dot product of E1 with itself, and if you recall, we deliberately set the magnitude of the basis vector for R, or x1 if you like, equal to 1 everywhere. There's no stretching of the radius basis vector E1, so G11 is indeed unity. Now what about the last entry, G22? This is equal to R squared. In other words, the dot product of E2 with itself is R squared. The interpretation that we're trying to follow is that G22 is only to do with the squaring of the stretch of the x2 basis vector. And if you think about it, that seems to be the case here. We had said that the x2 axis is the theta axis, and we had defined basis vectors for that axis, which had to get bigger at higher radii, and they were made to be linearly proportional to r, the radius. So it makes sense that the dot product of the theta basis vector with itself should be r squared, and that, therefore, is the G22 entry for the metric tensor of polar coordinates. Anyway, so far so good. The interpretation of the three independent numbers within the two-dimensional metric tensor which relate to the angle between the basis vectors at the point in the space and the value of what you might call the stretch of each of the basis vectors at that point seems to work. You should by now, I hope, be beginning to see that identifying the three parts of the metric tensor in this kind of way is a valid way to think about two-dimensional space. Furthermore, and this is very important, It is true even if the frame of reference is curvilinear and made up of wavy lines, like this. And even if the space itself is curved, each infinitesimally small point in the space essentially has straight line coordinates at some angle alpha to one another. The space could be flat and measured using curvilinear coordinates like this, or curved and measured with some kind of curvilinear coordinates. Either way, the same simple interpretation can be made. The metric tensor for such a curved frame of reference will almost certainly have different values everywhere in the space, or at least it will be a function of position, like this. And there will probably be changes of angle from place to place, as well as stretches and contractions. However, if we pick a single point in the space where the sizes of the basis vectors and the angle alpha between them are known, and if we substitute those values into these equations for GMN, we would get the 4 definite G values for that particular point in the space. Actually, perhaps we should say 3 G values. In fact, we'll show one of them in red to indicate that it is a repeated value. We will draw the specific point as a black dot here, and we'll make it easy for ourselves by choosing a point on existing lines so there's no need for interpolation. We can then illustrate the basis vectors E1 and E2 on the diagram at that point using these black arrows, which are shown as being tangential to the lines, and again we'll put the angle between them as alpha. Remember, these are the basis vectors at the centre of the black spot, an infinitely small point. We only draw the arrows extended so that we can gauge their size and direction. Now, the rule that we've just suggested can be applied to this point. The value of G12 and of course G21 will be the size of E1 times E2 times the cosine of alpha between them. The value of G11 will be the square of the magnitude of the basis vector E1 at that point, its size squared. If it's greater than 1, it will be stretched. If it's smaller than 1, it will be shrunk or compressed. And similarly, for G22, it will be the square of the magnitude of the basis vector E2 at that point in space, and we'll show the extent of its stretch or otherwise. So even this curvilinear frame of reference describing 2 dimensions essentially has 3 numbers at every point in the space, and those numbers in effect describe an angle and 2 stretches. And all of this rather simplified interpretation of the metric tensor applies to higher dimensions as well. For example, if we take 3-dimensional space, which may or may not be curved, then we can say that the metric tensor for a particular frame of reference being used to measure the space would once again depend on position, and it could be drawn like this. The lines representing the basis vectors could be bending all over the place in this 3-dimensional space, but if we home in on a single point in the space with particular values of x1, x2 and x3, the metric tensor would then contain 9 definite numbers related to that point. Actually, of course, there are only 6 distinct values here because these 2 are the same as each other, simply because the dot product of E1 dot E2 is the same as E2 dot E1. Similarly, these 2 are the same as each other, 1 and 3 and 3 and 1, and so are these, 2 and 3 and 3 and 2. We'll show one of each pair of these in red just to distinguish them. So with this 3-dimensional frame of reference, there are really 6 independent numbers that the metric tensor tells us about for this particular point in the space. What are the 6 things? Well, at the point under consideration, there will obviously be 3 basis vectors crossing through the point, something like this. And hopefully you can appreciate the 3-dimensional perspective here. E3 is supposed to look somewhat into the screen. I hope you can also appreciate that we will have 3 angles between those 3 basis vectors. And that all means that we will have 3 multipliers or possible stretches of the basis vectors, and we will also have 3 angles giving 6 independent measures altogether. And these will relate to the 6 independent G values in the metric tensor, which will be some mixture of the 3 angles and the 3 numbers, or the stretch and the multipliers. 6 numbers for 6 things. The 3 On the diagonal, g11, g22 and g23 are the squares of the sizes of the basis vectors e1, e2 and e3, and so they represent the three stretches squared. The remaining three numbers, g12, g13 and g23, relate to the angles and to the stretches, such that g12 is e1 times e2 times the cosine of alpha 1, 2, the angle between e1 and e2, and so on. And that way of interpreting the entries of the metric tensor is true for any frame of reference and any kind of three-dimensional space, flat or curved, providing you are homing in on a particular point in that space. So in one sense, we shouldn't be afraid of the metric tensor, apart from when we get into some of the real mathematics. The actual concept, at this level at least, is fairly straightforward. Of course, when we come much later on to four-dimensional space-time, we will have 16 entries in the metric tensor, each of which can depend on position, the indices running from 0 to 3. However, the same idea will apply. Homing in on a single point or event in the space-time means that we will simply have 16 numbers, or rather 10 independent numbers, for that point. Even though the fourth dimension of time, x0, will make many more further complications, we can still think of there being 4 diagonal entries of pure stretch or contraction squared at each point in space-time, and also 6 independent off-diagonal entries which involve stretches and angles between each pair of the various 4 directions, all of which adds up to 10 independent pieces of information in the matrix. Finally, putting time behind us for the moment, we did promise to take a look at an actual curved surface to see how this idea fits into that kind of thing. Consider the surface of a sphere of constant radius r, which was being measured using a frame of reference which we had called surface spherical polar coordinates. The two coordinates x1 and x2 here are the angles theta and phi. The metric tensor for the whole of this two-dimensional space can be shown to be, and we gave it earlier, as r squared 0, 0 r squared sine squared theta. Let's analyse this by using the way of interpreting the metric tensor that we've just been thinking about, angles and stretches. Remember, in terms of these coordinates, we took theta as x1 and phi as x2. R is constant on the surface. These entries in the metric tensor are essentially the same thing, and they're both 0 in this case. This means that the cosine of the angle between the two basis vectors x1 and x2, or theta and phi, is 0. That angle must be 90 degrees everywhere, and that of course is fine. We know that angles between longitudinal and latitudinal lines are 90 degrees. It's obvious. It's obvious, but maybe it still sounds rather strange. The angle between the polar theta measurement and the azimuthal phi measurement is 90 degrees. But hopefully you get it. Just think about it. So that's one of our 3 numbers accounted for, the one which takes up 2 entries in the metric tensor. Now look at this one, g11. This is the dot product of the basis vector e1 with itself, and is r squared, so in a sense the stretch of the e1 basis vector is r. In other words, the stretch of theta is r, but of course r is constant for this particular surface space, so it doesn't matter. It simply means that if the sphere were to be larger, then the theta basis vector would also be bigger. In practice, that would mean that the vertical gaps on the sphere, if I can call them that, would be bigger if the sphere were bigger. And that's obvious, so it's not really worth commenting on here. For our surface, with that particular value of r, it is of no consequence. But what about this one, g22, r squared sine squared theta? What's that all about? Well, forgetting about the r squared, because for a given sphere that would be constant, we should focus our thinking on the sine squared theta part of it. What is that signifying, and how does it fit into this way of thinking about the metric tensor entries? Well, by this way of interpreting the metric tensor, G22 is to do with the square of the size of E2, which relates to the angle phi basis vector, and showing us here that the phi basis vector seems to increase in proportion to sine theta. This sine squared theta will start to grow as theta increases from 0, at least until it gets to 90 degrees, and then it will start to get smaller. Remember that once an angle gets to 90 degrees, the sine of it starts to decrease. Let's say that again. The phi basis vector, x2 going around the sphere, gets bigger for bigger theta up to 90 degrees as you come down the sphere. So working from what we might call the north pole to the equator, the phi basis vector is increasing. And once you get past the equator, or 90 degrees, it starts to get smaller. Well, if you take a little time to think about that, it makes perfect sense. These basis vectors for phi going around the spherical surface up here will be smaller than those going around here, as they increase with increasing theta as you move down the sphere, until of course you reach 90 degrees, and then they start to go smaller again. And that really concludes all we need to say at this stage about metric tensors for two-dimensional spaces. We've looked at some for measuring flat space, and we've just looked at one for measuring a certain type of curved two-dimensional space, that of the surface of a sphere. Now, at the risk of jumping ahead of ourselves, and before we finish this video, it might be worth simply mentioning some four-dimensional space-time metric tensors. Don't worry about understanding these things just yet, but just accept what you see, and we'll get to thinking a bit more about them eventually. If we had a flat four-dimensional space-time and we were working with special relativity, with no mention of accelerations or of gravity, and if this were being measured using the simplest type of reference frame, equivalent to Cartesian coordinates, we would have what is known as the Minkowski metric. And one form of this can be written like this. The diagonals are G00, G11, G22 and G33. You'll notice that the G00 entry is -1, and that might be familiar to those who recall some of their special relativity, but if not, don't worry at this stage. Also, it's traditional once you get into relativity to use Greek letters like mu and nu for indices rather than m and n. And also you'll probably see this special relativity Minkowski metric sometimes designated with the letter eta rather than g, simply because it is quite special. It should probably be obvious from the ones in the diagonal that this metric tensor is indeed for a flat space-time and for a Cartesian type set of coordinates which are being used to make measurements of that space-time. There are no r's or thetas here, which would indicate that the flat space was being measured using some kind of equivalent of polar coordinates. On the other hand, once we get into general relativity and take into account accelerations and gravity, things become much more complicated. For example, for an uncharged, non-rotating black hole, one form of the Schwarzschild metric tensor can be written like this. Take a little time to look at this. You probably sense here that it is using a kind of spherical polar coordinate system. Not just the surface spherical, of course, because we're in 4 dimensions here, so we have 3 spatial dimensions and time. You will also realize that in this case, time is x0, radius r is x1, the polar angle theta is x2, and the azimuthal angle phi is x3. In this situation, the origin will be at the center of the black hole, and there's a kind of rotational symmetry of some sort, so that the most relevant spatial variable gravitationally is r, or what we might call x1. Notice that these 2 entries in the Schwarzschild metric are the same as we had for the only 2 entries in our surface spherical polar coordinates earlier, and they relate to some measurement around a sphere of radius r involving theta and phi. As in that situation, they tell us that G22, which is the dot product of the basis vector E2 with itself, is r squared, so that the stretch of theta is r. Similarly, G33 is to do with the square of the size of E3, which relates to the phi basis vector. which, as we discussed, varies as sine squared theta, and therefore gets bigger for bigger theta, at least until you get to 90 degrees, whereupon it gets smaller. These two are fairly straightforward geometrical issues, whereas these two, the time element x0 and the radius element x1, both contain the universal gravitational constant g and the speed of light. Now, from what little you know about black holes, you might expect theta and phi not to affect things gravitationally. Different places at different angles on a sphere at some given distance r from the black hole would surely all be the same gravitationally speaking, except of course for the radial direction. However, you would surely expect that the distance away from the black hole, the radius x1, and of course time itself, because of relativity, would be crucial in the way things are measured. And the metric tensor is all about the way things are measured. Okay, so having seen a couple of metric tensors related to relativity, we now want to turn back to simpler ideas without time, and of course without accelerations or gravity. This video number 6 has been an introduction to the metric tensor for coordinates used to measure curved spaces. In the next video number 7, we will introduce the important concept of the covariant derivative, which will include, of course, the introduction of the idea of the Christoffel symbols.